Okay, so we last lecture we were computing this case, right? So we want to get or to understand what happened with this case, right? So this is my task. Remember this, okay? So I'm going to do this. You read. Everyone can see it. Okay, so the first case that can you see this here? Here? This good. Okay, so we have this case, and now we have this case. Okay, we have this and this. Okay, so just to put what we have so far, we get this. And now, if you see, we get this kind of. As you can see here. You see? So now, according to this, I suppose everyone got the here, please. As you can see here, you have now, before we have three energy levels, when we put two atoms together, we have six energy levels. For this case, right? For the case exactly the same potential, if we have the same V sub zero in both cases, right? V sub zero. And this is the thickness of the well is exactly the same, and the barrier in this case is B, right? You see? So we have this. Okay. So the first result when you put two identical atoms together is to have this. You see? How do you know? How we know this? Because of this. Here is not clear to see, as you can see from the plot, maybe it's not that straightforward to see that there are six levels, right? So as you can see from here, you see here that here there are you see here is not clear that in fact there are two levels, right? But here two and two. But if you put this command here approx loops here, you are going to have in total six energy levels, as you can see here. Okay? So everyone has replicated to here, right? Okay.
I have a problem with the numbers because.
Yes, let me check.
Turn.
Let me check, please. You should have exactly the same, but I'm going to pause this here. Okay, now we are going for the level one. I just copy paste from the previous one. Yesterday, I just leave it level one. So the only thing you have to change here is this here, 8. You have to put here 8, 8, and that's it. You see? The same here, please. You have just to add comma, B goes to LB. That's it. The rest is exactly the same. And the plot, the only thing you have to change here is that you go from, what is this? I think it's 3.5 here. Let me see. And the plot here is, again here, please don't forget to put here LA, comma, B goes to LB. That's it. See? And the plot goes from minus 3.5 to 3.5. And that's it. Look this, we have this. Okay, everyone take here, please, before I continue. So from this, we have this. So the question is, if I put one electron in this system, where will be the electron? Steven, if I put one electron here, where do you think will be the electron? Here, or somewhere? Huh? But electron is only one. Anthony, I put one electron. Where should be the electron? Then I put one electron. Where should be the electrons? Okay. Buddy, I put one electron here. Which should be the electron?
No, I would say possibility the electron is safe and when a atom or an atom.
Okay. So yeah, it's correct. So remember, this blue line is the wave function, and the green one is the probability density, probability only. So it means that the electron could be anywhere, but it's more likely to be either in this part of the well or in this part of the well. We cannot predict in which part exactly. It's only probability. Remember this. So don't be confused, because some students are tempted to say no. If I put one electron, I say no, I would like to take the right because I like right. Right? Or I prefer the left. In fact, you cannot say anything, right? Because even the electron could be found outside of the well, or the more interesting, in between the wells, in the forbidden region. So you see, this is barrier penetration on the right, on the left here. And here is a tunneling effect. It's exactly the same origin. Okay? The only difference, because here there is a finite width of the potential. That's the reason we have this kind of we call tunneling, right? And this is the onset. That is the origin of any chemical bonding. The origin of any chemical bonding is because of this. See? So okay, so remember, please again for the last time, please, this time, please remember, we have, yes, then. Again?
What is the same for calculating the
The probability, you mean the green region?
of the electron can be everywhere?
Yes, exactly. But this probability tells you that if you do experiments, along all the experiments, you're going to find that in most of the cases you're going to have either here or here, but it's not 50-50. You may think it's 52, no. It is around 40% here, 40% here. So it's 80% to find it in this region or in this region of the system, but there is a small probability to find it here, also here. And because there is a probability to find electron here, it means it will create this what we call, this is basically the origin of the covalent bonding. Okay? So this is the only probability. This probability allows the system to start to bond to this. Okay. So let's see. Let me see now. Let's first of all integrate. We're going to integrate this. Remember, the only thing we have to add here is this one, comma, P goes to LB. If you integrate this, you have to have 1. You see? You get 1. What is the probability of finding an electron? Let's see, what is the probability of finding an electron within this barrier? So from minus B over 2 and B over 2. Let me see what is the probability of finding an electron in that region. Okay, I can take this. I want to know what is the probability of finding an electron in this region. Look this, in the forbidden region. Okay, so let me see. So this is the same, please, comma. I'm going to copy this, comma, this from LB minus LB, right? Because this is the width of the potential value. Is 0.016, So if you like, this is one way to quantify how strong is the bond, right? You see, very interesting. So this is the intersite electron density, or the electron density within this within this energy. But also we can, okay, I'm going to add this here, please. So what is the probability of finding electron in this region? Let's say either on the left or on the right. I'm going to take on the right from minus here is okay, left. On the left, I'm going to take minus V over 2 minus A till this region, right? From here to minus V over 2 in this region. So I want to see what is the probability of finding electron in this part of the potential, in the left part of the potential.
So basically I copy, please, very simple, copy this, paste it here. And you just put from X from minus LA minus B minus LB over 2. You see? Is this 0.48? It's not 0.5, as you can see. So the probability of finding electron in this region, please, it is not 0.5, it's 0.48, right? And also there is some probability of finding electron outside of the well. So let me see what's the probability of finding when X is, let's say, on the right here. What's the probability of finding electron in this region above this potential, right? And the outside of the potential will be when X is bigger than this, right? When X is bigger than this, than A plus B over 2. What is the, let me see. So again, we are going to have the proof of the A LA plus LB till infinity. You see, it is this. It's non-zero, as you can see here. So the probability of finding electron out in that and the right part of the potential here is non-zero. Is this? So it means this is the bar again, barrier penetration, right? So there is some kind of barrier penetration and so on. Okay, so let's continue this. What is this? Now, what is the probability of finding electron? I did it here. Sorry. So this is here, this comes here. So it's just to put this. Okay, and minus A minus B. It's just I'm just cleaning up this. Okay, so I did this already, so no needed. So I have just to edit this anyways. Okay, so now let's find the expected value on the position. This one. I copied from the previous section, so we have this. And we have to add this only this, comma, B goes to LB. And that's it. So the expected value in the position is 0. In this, but for this case. The X, let's go for the X square, please. So the only thing you have to add is this, please. Don't forget this. You have to add this, and after this. X squared is this. Then the uncertainty on the position is this. The uncertainty on the momentum, please. You have just to add this. You have this. Just you have to, that's the easy of this because you can. The uncertainty in the momentum is this. And therefore, the Heisenberg uncertainty is 1.6. You see? This is for the first level. So I repeat it here again what I did, please. So now let's find the uncertainty delta X and uncertainty on the position of delta X and the uncertainty momentum delta P is like this. The only thing I did from the previous case is just I added this part, nothing else. Okay. The next one also I added this part here, this, and you find this. Okay, just you have to update this. On momentum the same, please. I don't have to change anything because everything is fine. And the momentum square is this. Then we have the Heisenberg uncertainty is this. See? So we expect that value should be bigger than 0.5. Yes, it is bigger than 0.5. Okay. I'm going to pause this for the moment. Continue. I'm going to continue, please. And again, the same, please, here. So you have just to correct this, put this, and you have the kinetic energy for this energy level and the potential energy, the expected potential energy for this energy level. We have this. And now if we add both, please, you are going to have this and you replace this is this, right? So you see, this is for any type of, in any case, it's exactly this. Okay. Let's go ahead, please. Now we have level 1, please. We go for level. We have to do 6 cases, please. I'm going to 1, 2, 3, 4 pieces. I'm going to change this 2, 3, 4, 5, and 6. And you change here just to 2, here to 3, here to 4, here to 5. So simple. Here to 6. And now I select all of them, the missing one here till here. Shift enter. And now we can check this from I to 6. There it is. Control S. Don't forget to save it so you. You will take here, please. And now we are going to do, and now we are going to take some time to discuss this, please. Okay, I'm going to wait a little bit. Okay, so look at the wave function for level 1. For level 1, you see, there is the probability of finding electron inside of the forbidden region of the barrier never becomes 0. It's very small, but it never is 0, right? So it means that we call this state, this electronic state, bonding state, right? But look for the level 2, please. Let's go for level 2. In level 2, look what happened with the wave function. The wave function becomes 0 in the middle, you see? So it means that the probability of finding electron in this region, in this part of the potential is 0. So for that reason, we call anti-bonding state, you see? This is anti-bonding state. Let's see for level 3. Level 3, look what happened. What do you say? That body, the level 3, is bonding or anti-bonding, and why? Why was bonding? Correct. As you can see, since the wave function does not become 0 here, so we call that bonding. So let's see level 4, please. So Diane, what do you think? Level 4, what happened with level 4? Is bonding or anti-bonding? What do you think? Huh? It's anti-bonding, right? Because you see, correct. So it's anti-bonding because, as you can see here, the wave function becomes 0 inside of the forbidden region, or the energy, the potential barrier. Okay, so that's it. So we are going to have, you go upper levels, you have this, and you see that is with the stability of the material will be how many bonding states you are going to have, right? So if you start to occupy more anti-bonding states, that system is unstable, so will split. But if the system has more bonding states, the system will be stable, so will be forming a molecule and so. Okay, that is the case. I suppose the theory of orbital molecular tone, right? The user is kind of theory. You see, this is the nature of the bonding and anti-bonding, right? And you have to be, that is important because it gives a stability to the system. Okay. Any question here? Somebody want me to repeat any part, please? Somebody need to repeat this. If you see level 5, Steven, level 5 is bonding or anti-bonding? It's bonding, you see? And you see, can you notice the electronic density in the forbidden region? You see, it increases. The higher is the energy, it increases. Now I have a question. For instance, you have this. Right? Let's suppose you have this plot of two wave functions. You have this wave function 1, let's suppose it's like this. And wave function 2 is like this. The question is, which wave function will have higher kinetic energy? This or this? Higher kinetic energy. This is x, by the way. This is x. And this is the wave function, right? So which wave function, which of the wave functions, this is the wave function A and this wave function B. Which wave function should have higher kinetic energy, and why? Angel, which wave function should have higher kinetic energy? Just by looking at the wave function.
Just looking back.
Which one?
The second,
The second?
by the, wait, number. I think.
Okay. Somebody, do you remember this? Which one? The second? Somebody has a different answer. Anthony, which wave function should have higher kinetic energy? The second. Okay, see, Kurai, do you agree with everyone? Correct. So when you see a wave function and it has more nodes, so it means it has higher kinetic energy. How you can see? Just remember this case, please. Look this case here, the summary. You see? The higher the kinetic energy, in this case, has higher energy level, and you see there are more weighting. You know, there is more nodes, as you can see here. 1, 2, 3, 5 nodes, and so on. You see? So the more nodes it has, the wave function, more higher kinetic energy will have the particle, right? And that's it. Well, now let's go. Any question here, please? Somebody has any question? Want me to repeat this? You know, so we have checked. So far, we have checked bonding and anti-bonding states, and also we have checked for instance, the kinetic energy of the wave just by looking at the wave function, what is the kinetic energy, right? So this is a typical question. For instance, if you are in a test in quantum mechanics, this is a typical question: which wave function should have higher kinetic energy, right? So that is, remember, it's more waving, more high kinetic energy. Now, this is a very nice example because here we can also infer what is a core electron and what is a valence electron, right? Core electron, when the electronic density in the barrier is very, very small. You see? So these electrons basically does not help too much for bonding. And that's the reason we call core electron. They are practically localized in either one atom or the other. The higher energy it has, you see what happens with the wave function, they start to be more very localized. See? So it means that these electrons, in fact, are tunneling. Well, here electrons are tunneling, but the tunnel is very, very small, neglected. But here is very high. So this is the ones that provide the stability of chemical bond. Right? Remember this, in real atoms, this potential is thousands of electron volts. So it means that this, if you see the wave functions of the S electron, because there are S electrons, almost there is no electronic density in atoms. That's the reason we don't consider those electrons for chemical bonding, right? And the properties of any type of solid or material belongs to the valence electrons. Electrons are more has higher kinetic energy, and therefore, of course, and they're localized and they produce this kind. Okay, very important. You know, this is we are going to compute even in a higher, more sophisticated way, and the properties are the same. No? That's the reason we are going to consider only the valence electrons. Okay? Of course, there are codes that will use all electrons, to be more exact. But remember, you don't miss the properties of material if you parameterize these for electrons and just you use the valence electrons. You see. Okay. So you can see also, look this, you can see the electronic density. Let's check the electronic density in the barrier. So I'm going to collapse this, please. Let's check the electronic density in the forbidden region, right? In -B, in between. Remember that we computed electronic density in -B. Where is this? Here. Look this value. Let's check the electronic density in this. Look this. The level 2 is anti-bonding state. It's 0.009, right? And look for the bonding state. Let me see where's the bonding state. Is a little bit higher, right? It makes sense. 0.016 versus 0.09. You see? So from this, if you want to quantify the contribution to bonding, you can check this value, right? It's basically electronic density in between the two atoms across the barrier, the potential barrier. See? So this is the way that we can even quantify some properties of the material. Okay. Questions if here somebody puts. And of course, look what happened with let's see this electronic density for the upper, the highest kinetic, level 6, let's say. In level 6, that value becomes, look this. Well, this is antibonding, but anyways, let's see the antibonding, the electronic density is 0.066, 0.07. Of course, the level 5 is bonding state, it has to be higher. And there it is, right? So like this, 0.21, see? So the higher the kinetic energy in the system, these electrons become more delocalized, and we are going to call them the valence electrons, right? So that is questions here, please. If somebody has any questions? No questions? Okay, I'm going to pause here for only one. So yesterday, we did this, right? We have an atom with 5 electrons. Now the question is, here, how many electrons? We have 2 atoms with 5 electrons. How many electrons? 10 electrons, right? So, what will happen when we have 10 electrons, please? What will be the electronic structure will be, we have to put 2 atoms, two electrons in each energy level, right? So some students are tempted to put like this, 2 electrons here, so I will put 1 here, and I put 1 here, No. Not correct. If you put 2 electrons in the first energy level, here we are going to have 2 electrons. Here we are going to have 2 electrons, right? We have to do 10 electrons. Here, 2 electrons. 2 electrons, right? So 2, 6, 8, 2 electrons. You see? So the highest occupied state, or in this case, since we have 2 atoms, we have molecular. So the higher occupied state, we call it sometimes, in the chemists, they like to call it HOMO, right? And the lowest unoccupied state, in this case, is molecular orbital, right? Why molecular orbital? Because we don't have one atom, we have a state that it's depending on the position of the 2 atoms, molecular orbital. You see? So in this case, the HOMO for these 10 electrons will be the level 1, 2, 3, 4, 5. The 5th energy level is the HOMO, and LUMO will be the 6th energy level. See? So that will affect to anyone who is doing electronic structure, has to know this concept. Doesn't matter if you're chemist or physicist, we have to speak the same language. Okay, so we have these 10. So the question is, let's compute the total electronic density if this molecule has 10 electrons. Please give me the answer. First person to give me the answer, 3 points, please. What is it? Okay, so the total electronic density, electronic energy will be just to add the eigenvalues of the energy levels, multiplied by 2 because there are 2 electrons in the energy level till 5, 10 electrons. The kinetic energy exactly the same, we go I from 1 to 5, and the potential energy will be 1 to 5, right? So we have this, we have this value, and this is the potential energy. If we add both values, look what happened with the total energy on this, exactly the same. See? Okay? Now we are going to add something extra, please. It says that for this 10 electron, this molecule with 10 electrons, 10 electrons. Right? With this molecule with 10 electrons, A. What is the HOMO? HOMO. We call it the highest occupied molecular orbital. And LUMO, the lowest unoccupied molecular orbital, right? What is this? For this case system, right? And B, let's answer B. What is the photon frequency? Photon frequency. What photon, sorry, what photon frequency is needed to excite, okay, to excite one electron from the HOMO to LUMO. Okay. So the answer, what is the answer? What is the HOMO, please? Very simple, right? So answer A, HOMO is the level of 5. N is equal to 5, right? That is the HOMO. So how to compute this? Basically, you divide 10 divided by 2, that is equal to 5. That will give me the energy level. This is the integer value of this, right? So for this. So let me see. So the value of this, let me see, it is bonding or anti-bonding. It's bonding or anti-bonding. What do you think? Let me see, it's bonding. It's bonding or anti-bonding? Steven, it's bonding or anti-bonding? It's bonding, right? You see, because there is no nodes in the forbidden region. The lowest, the lowest, the lowest LUMO is for n equal to 6, right? Equal to 6. And let me see if it's bonding or anti-bonding. Level 6, we have this. It is anti-bonding, you see? So level, the LUMO happen for this case, it is anti-bonding. Okay, we have this. Okay, what else? The photon, no, so let's complete this. The photon frequency, the photon energy to excite one electron from HOMO to LUMO is this, right? So first of all, we have to compute what is the energy, right? So would be this delta energy. I'm going to put like this is equal to, right? That will be but let's first of all, since we need to compute in hertz. So let's remember what this is. So we can ask this one Hartree to joule. So we want to compute, we want to know what is 102. So this is the conversion. So that's what we are going to compute like this. So it will be R-val 6, because remember that is the LUMO minus R-val of 5. So that is will be in Hartrees. But one Hartree is this value, so we have to compute by this, right? So 4.374 times 10 to the minus 18. So that will be the value in in joules, sorry, in joules. Now, how to compute from that energy? How you can compute the frequency of this photon? That has this. So the energy to excite one electron from the COMO to LUMO will be this energy. That is in joules. So from this, how I can compute the frequency? Remember? Remember what is the energy of a photon? What is the definition? Right, this is h bar omega or h times n. Therefore, the frequency is equal to E over h. That's it, right? So let's compute this. So we're going to compute this. So basically, we have to solve it like this, right? So will be this energy. That the question is this is equal to h times n, right? So I solve this in f, right? And here I have to replace h but the value in international unit, 6.626 times 10 to the minus 34. So F is 2.66 times 10 to the 15 hertz. We can infer what is the color even. So let me see. This times 10 to the 15 hertz. See, this hertz. So let me see what Mathematica tell me about this value. So it is far ultraviolet, this one. So we need that type of frequency that is in the ultraviolet to excite this in this law. See? Questions here, please. Somebody need my help in something here, please. Questions? No questions? Angel? Okay, that's one second. I'm going to. So next thing that we have to infer is this, What is the cohesion energy if of this system? This system. What is the collection energy in this system? Right? Remember, this system has 10 electrons. So what is the definition of the cohesion energy? The definition of cohesion energy is this, right? So the cohesion energy is just the energy you need to split apart the system, right? So the final, so if you like, this is the molecular state minus the energy when the two atoms are far away. So we're going to use this definition. We're going to use this, by the way, in the hands-on sessions, and also I will ask you what is the cohesion energy for the system you have to compute in the midterm project, a solid, but that's this concept is very general. So the cohesion energy is the energy of in this case of the molecule divided by so it's the energy of the system divided by the number of atoms. So the energy of the system per atom minus the energy of the atom, right? So the energy of the isolated atom. So let's compute this, right? What is the cohesion energy? So with this, we need to find what is this. I'm going to put this. What is the energy of the molecule? Please, we know this. What is the energy, the total energy of the molecule is this, right? So we computed already the energy of the molecule is here. Is this 26 point, right? That is the energy of my molecule. What is the energy of the isolated atom? I'm going to play this atom. What is the energy of we compute this? Please remember the previous section. Let's check what is the energy of the atom. Here, this. Remember this is here. You go to the end, it was here. Remember, this is for it was this value. Okay, so I go to is this value. Okay, therefore, Recuperation energy, I'm going to put like this, is equal to this. Is equal to the energy of the molecule divided by 2 minus the energy of that. Is this. Okay? Don't forget to save it. And we're going to discuss what does it mean this. Well, anyways, I need everyone, please. Okay. The energy, right? In the system, you're going to compute, let's say, with math, Orca, you're going to find that the energies of the systems always will get negative. And it's related with this, you know, because we always put the reference level at the infinite. When R goes to infinity, the potential goes to 0, you know, the potential of R, when the limit, when R goes to infinite, it is 0, right? But I can do this just by convention because it's more convenient, but you see, I can shift this, my new, I can collect this, you know, in such a way that all the energy is positive. What is the important point is where is the lowest energy? So this is the equilibrium position, let's say. In this case, since the potential is 0, right? That's the reason we have this case too. Now, based on that, it means who has higher, and with respect to 0, who has higher energy, you see? So, in this case, so in the case you have to ask, if this is a 0, who has higher energy than 0? Or what happened with this with respect to the 0 level? Because both are positive. In this case, if you divide this by 2 and compare with this, we are going to see this divided by 2 is lower than this. So the energy of the atom is here, and the energy of the molecule is here. So the energy of the atom is a little bit higher than the molecule per atom. Since it's 0, so if you subtract this value minus this, it's going to be negative. Okay? But what I like to analyze is the energy, right? So with respect to energy level, energy reference level, what is my energy reference level for this system is 0. With the first 0, let me check what is the value of energy. What is the energy of the atom is 30 points. So much here. Energy of the molecule divided by 2 is less than 30 points, so it's here. Okay. So it means that in nature, always the system try to go to the lowest energy possible. So in the system, the two atoms at the end will combine with one. But here, we might have it the other way around. So you can check. I leave it to you guys to check this. Do the case of 4 electrons. Now you can compute. Now you can come back and compute for 4 electrons and these 8 electrons. In that case, you are going to find maybe that is the opposite. It means that if I take from here 1 electron from the atom, or if you like, if I take 2 electrons from this system, right? So I will have 8 electrons. When you compute this, you're going to see, just I leave it to you guys to check that the energy of the atom is here and the energy of the molecule is here. It means that this system is not stable. You can check by yourselves now. Let's check with later. At the fundamental level, what is this? Is because how much bonding states you're occupying, and not only that, how much electronic density is in between this inside of the region. That will give more stability, right? So look, if I add 1 extra electron here, there will be a problem because I will add some anti-bonding state. So the system will become unstable. So it might be will split. Okay. Questions, please. Okay. So I'm going to pause this, and I think we are ready to continue with the